Welcome back to Learning with the Fosters and our front porch in Cabo Rojo, Puerto Rico. We're going to go over the homework today regarding our discussion on the real number line. But before we do, Learning with the Fosters has a very exciting announcement to make. There are 2 new members to the Learning with the Foster team, household, family. Our goat Valentine just gave birth to twins, a little boy and a little girl. They're incredibly cute and adorable little goats. The boy's name is Ignacio, and the girl's name is Encarnacion.
Our new members of the family. Val just gave birth just a few minutes ago. Getting some leche. What a good goat Valentine is. Uncle Snowy's looking.
Thank you, Lord.
Thank you, Lord. Look at the goats. Mama Valentine.
So if you remember one of the homework assignments from back in our lesson talking about subsets, you'll recall that we had a problem where we were supposed to construct a Venn diagram to demonstrate the set relations between the inhabitants of Casa de Foster. Well, now we have 2 new ones, so we can update that information. So if you'd like, you could go back and rework that problem and update with new information. But let's turn now to the homework for today's task regarding the real number line. Our first task was to consider this number line and to correctly insert either less than or greater than symbols into each of these to make each statement true. And again, just for review, we denote less than like this, and we denote greater than like this. So as we read from left to right, if this was, let's pretend this one turns out to be C is less than E, we would insert this symbol. It would be read C is less than E. This one would be C is greater than E. And again, the helpful way I remember, still stuck with me back from whatever grade we learned this, I think 2nd or 3rd grade, that the big mouth opens towards the larger of the quantities, that like the alligator is going to eat the bigger portion. So let's see how we did with that. C and E, these are points. We're dealing with points on the line again. So here's C, here's E. Well, how do we know what one's greater than or less than? There are no numbers. We're kind of used to working with numbers. But remember our discussion, our number line is oriented so that the quantity increases in the positive direction as we move from left to right, and increases in the negative direction or decreases as we move from right to left. So we're looking at relations here relative to each point. So here's C, here's E. Well, E is increasing this side. That means it's getting larger. It's growing in quantity in the positive direction. So C is less than E. So what symbol do we use? Well, we want the big one to have the big mouth. And that's great. And it's good to remember that way, but it's also important to get to understand these symbols and be able to use them without necessarily stopping and thinking about alligators. We want to know what's going on. C is less than E. What symbol do we use? This one. So this makes this a true statement. Point C is less than point E. Very good work. All right, let's consider this one. A and D. So here's point A. Here's point D. Well, kind of the same type of scenario, right? D is increasingly positive, which means it is larger than A. So A is less than D. Or we could look at it in reverse and see that A is decreasing as it moves in this may sound odd, in the increasingly negative direction. Or in other words, farther away from our origin in the negative direction. So A is less than D. How about B and A? Well, here's B. Here's A. We've dealt with A thus far. But what is B relative to A? Well, B is this direction of A. So we would say that B is what? Greater than A. So we are greater than sign. So we looked at A with respect to D, which would have been the same as A with respect to D. So when we're talking about A is less than D, but when we're discussing B in relation to A, B is greater than A. All right, how about C and B? Well, here's C, Here's B. These two are quantitatively closer than some of the others, but still there's a difference. They're not equal. They're not the same point. So one is going to be farther this direction than the other. Or in other words, one is going to be greater than the other. In this case, C is greater than B, and that's what we're asked to find. C is this side of B, so C is greater than B. How about D and B? Here's D, here's B. Well, D is this side of B, so D is greater than B. How about E and C? Here we have E, here we have C. Again, same or similar scenario, although the distance is different, but we're not dealing with that right now. We're just saying what is greater, what is less than. E is greater than C. Now we could just as easily say C is less than E, but in this case we're looking at E first. So E is greater than C. But we'll notice that saying E is greater than C is equivalent to saying C is less than E. Very good work. Let's move on to our next task. Now that we're warmed up a little bit, our next task is to take these points corresponding to numbers, remember we talked about that, and graph these on a real number line. So the first thing we'd have to do, of course, is to construct our real number line. Remember these arrows we're using to denote that it extends infinitely far in the positive direction and infinitely far in the negative direction. We need some sort of origin, right? We talked about that 0 is a great way to do that. So we will mark 0 as our origin. Now, we could just start plotting these points. We could say, all right, negative 13 over 4 is on the negative side, kind of guess where it is. But it'll help us kind of like a ruler if you have some spaced out evenly marks. Well, we talked about how the integers act as such. They are spaced out with the same step, so to speak. So let's write in our integers, briefly looking at about what we would need. So we'll list our integers. This will give us kind of a guideline on where to place these points. All right, we've got not a to-scale number line, but we've got a number line nonetheless that will allow us some working room to somewhat approximately plot these points. So let's look at it. Point A is equal to the number or corresponds to the number. Remember, we're looking at numbers, our points on the line. 4.0001672, and this decimal keeps on going forever without repeating, without terminating. Therefore, it is an irrational number. Very good. Even though we have a few repetition right here, it doesn't repeat on forever. So this is an irrational number. Where would we plot this? Well, it's a little bit, a very little bit, positive side of 4. It's a little bit larger than just simply the integer 4. So for our purposes here, our precision here, we can simply plot this, about right here. And so that is point A. Very good job. Let's look at the next one. Now this is an O, not a 0. This would be a non-true statement if this said 0 equals negative 13 over 4. Rather, this is point O is equal to negative 13 over 4, or negative 13 fourths, a rational number in the form A over B, where A is an integer, namely negative 13. B is an integer, not 0, namely 4. So where would this go? Well, it's on the negative side. Now remember when we talked about converting fractions to decimals or simplifying fractions and all that kind of stuff. What would be an easier way to look at this? Well, one way to see this is negative 13 divided by 4. So let's do a quick negative 13 divided by 4. It's going to be a negative number. How many times does 4 go into 13? Well, 3, because 3 times 4 is 12, with a remainder of 1. Decimal, bring this down. 0, how many times does 4 go into 10? Well, twice, without going over. 8, 2, 0, 4 goes into 25. So the decimal, negative 3.25. So that makes it a little bit easier to plot. And there's other ways we could look at this to make it simple as well, but we'll just stick with this since we worked on this. So negative 3. Now where does this 0.25 go? It's a little bit larger. If this was a positive, 3.25 is greater than 3. Remember, these are negatives, and the negatives increase in the negative direction. So negative 3.25 would be less than negative 3. So on to the left of negative 3. So if this is negative 3, negative 3.25 would be if we divided this into fourths right here, to the left. And actually, by dividing these into fourths and simply counting 13 in the negative direction would have been another handy way to find out where this approximately would be plotted. But there we have our point O. Next one, point E. Point E is equal to 0. Well, 0 is easy. That's our origin. This is point E. Very important point in this case. Next one, D is equal to 3/5. Okay, well, I guess we've been talking about this. What type of number is 0? Well, it's an integer. It's also a whole number. It's also a rational number. D, 3/5, this would be, of course, be a rational number, a fairly obvious rational number. 3 and 5 are both integers. So where would this be? Well, it's less than 1, so it's going to be somewhere in this continuum space between 0 and 1. If we were to divide, let's look at this one a little bit differently. Instead of converting it to decimals, we could divide this space into 5, and this would be the 3/5 over. So 1, 2, 3. So somewhere approximately there. Point D. Next one, I is equal to negative 7. An integer, a rational number. Fairly easy on this one. In fact, the integers are our markers to kind of keep us somewhat spaced correctly. So negative 7. This is point I. Next one, M. M is equal to 6. Another nice integer. Aren't I nice on this assignment? 6 right here. This is point M. Next one, L. Looks like an irrational number to me. The decimals never repeat. They never terminate. This is going to keep going on and on and on and on and on again. So point L is 5.32168. Boom. So where would that be? Well, it's a little bit greater than 5. A little bit greater than 5 1/4. So here's 5. So maybe somewhere about in here would be close to 5 1/3. We have point L. Our next point, alpha, the Greek letter. We're going to get used to using Greek letters somewhat throughout this course. The rational number, 28 over 4, well, how do we plot that? Well, we could divide each section into 4 and count 28, or we could look at this. This is one way to look at this is 28 divided by 4, which is 7. So we see an integer, a rational number. Remember, integers are subsets of rational numbers. I know what happened. This is missing a negative sign. So let's fix that right now. This is not L. My bad. See the all-importance of negative signs. This is supposed to be negative 5.32168. So here's negative 5. Now here again, this kind of tricky decimal. What side of 5 will this be on? Well, negative 5.32 is less than negative 5. So it'll be to the left of it, about negative 5 1/3. So here is point L. That's looking better. You'll see why I noted that that's wrong in just a minute. Maybe you've already put it together. Okay, we did point alpha. Next point, V. Point V is negative 0.6 repeating. Remember that repeating bar. So this is going to be 0.666 forever. So that's point V. Irrational or rational? Right, rational. Rational numbers, decimal expansions, either terminate or repeat forever. Or you could say they just repeat forever because the terminating ones have those trivial zeros that could go on and on and on. So where's point V going to be located? Well, negative 0.6 repeated will be before negative 1, a little to the negative side, to the left of 0.6. So right about here. Point D. So we have successfully plotted our points. Before we move on from this problem, though, let's notice some interesting pattern. It's always good to look at things and not just move on once we're completed with the task. Let's see if our grand picture tells us anything. Well, to me, I look at this and see a great mathematical truth, one that is fundamental to the core of all reality, something we don't want to miss over. Let's consider these points. I, L, O, V, E, D, A, M, and alpha. And remember, alpha is the Greek letter that is phonetically sounds like our A, or the transliteration of our A. Look what it spells. I love Dhamma. This is the most important mathematical truth we will ever be able to look at in this course. All right, now that we discovered the greatest truth in mathematics, we can move on to smaller matters, the next portion of our homework assignment. All right, our goal again was to consider each statement and make each statement true by correctly identifying either a less than or greater than symbol. So let's look at the first one. Negative 0.6 repeated and negative 13 over 4. Well, we could convert this to a decimal or this to a fraction and compare, but we already have done a lot of the work with the number line, and this is what we're focusing on, is the number line. So let's use our number line to kind of solve some of these difficulties. First glance is if you're asked what is 7 and 1,000, 7 is obviously less than 1,000. Well, these are a little less automatic, perhaps. At least they are for me. So let's use the beauty of our number line that we already constructed and plotted to assist us in solving these. Negative 0.6 repeated is right there. And negative 13 over 4, remember what that one turned out to be, here. So B is on the more positive side than O, so negative 0.6 repeated is greater than negative 13 over 4. Now again, at first, if we kind of lose track of these negatives, that may seem counterintuitive, especially if we go ahead and turn this into a decimal. We'll get negative 3.25, which we did. And if we lose track of how negatives work, we could say, well, 3.25 is obviously bigger than 6, or larger than 6, but remember, the negatives expand that direction. So using the number line helps us sort out some of those errors so we don't make them. So negative 0.6 repeated is greater than negative 13 over 4. How about 0 and 3/5? Here's 0, here's 3/5. 0 is farther on the negative direction, 3/5 is positive, so 0 is less than 3/5. Next one, 6 with respect to 28 over 4. Well, here's 6. Again, at first glance, these are kind of like, well, I don't know. What does this turn out to be? And if you're not too quick on multiplication tables, which I'm not the fastest computationally, you maybe not know automatically which is greater, which is less than. Well, here was our point M, which was equal to 6. Here's our point alpha, which was equal to 28 over 4. Alpha's this side, farther along in the positive direction than M. Therefore, 6 is less than 28 over 4. And again, remember, 28 over 4 is another way to write 7. 28 divided by 4 is 7. So 6 is less than 28 over 4. Negative 13 over 4 with respect to negative 5.321568. Well, negative 5.32, etc. was our point P, and our negative 13 over 4 was our point O. So, or excuse me, L, not P. I don't know where I got P from. L and O. So here is negative 13 over 4. Here is negative 5. So O is greater than L. It's farther this direction. So we can denote that as negative 13 over 4 is greater than negative 5.32168, an irrational number. And again, remember, if we lose track of our negatives, this one we may quickly, in our haste, get it wrong by thinking that 5 is greater than 13 over 4. But remember, they're negatives. We're expanding that way, the negative direction. So you see where the number line helps there. All right, I think this was a fairly, at least relative to our last few homework assignments, I think this one was a little bit of a break in ways, intentionally so. So we just have one problem left to consider together. A very interesting one, I think. So let's now turn to that. All right, last task of the day. I think this is a fun one. Consider any real number a and b, and a is not equal to b. So you have two real numbers, a and b, any that you choose. Does there exist a real number c such that, and I hope you had fun deciphering this if you're unfamiliar with it, a is less than c and c is less than b? So what would that look like? Let's do a little mini example down here. Here we have a number line. We've got two points A, B, and C. A is less than C, and C is less than B. So B is going to be the greatest of all of them. Here's B. C is less than that, but greater than A. A is less than C. And by default, less than B as well. Because if C is less than B and A is less than C, then A is going to be less than B too. So in other words, this is a little bit more precise and convenient to write what we were describing in our first few lectures when we were talking about, say an integer between 20 and 25. Now we can say it, C is going to be between A and B. But not A, right? And not B. We'll look at the notation for that in our next lesson. But A and C are not equal. C is greater than A. C and B are not equal. B is greater than C. So C is any real number between A and B, excluding those endpoints. Not A and not B, but all real numbers in between. So that would include, on this little drawing, all the real numbers in between, but not quite counting A and B. All right, so let's continue reading the directions. So consider any real number A and B, and A is not equal to B. Does there exist a real number C such that A is less than C, C is less than B, or C is between them and not equal to A or B? If so, consider A and C. Does there exist a real number C sub 1, remember we talked about that notation a few lessons ago, such that A is less than C sub 1, which is less than C. Or in other words, C sub 1 is in between A and C, but not being equal to either A or C. We'll deal with this part last. So let's work through this slowly. I think this is a fun problem. So we get to choose, consider any real number A and B. Now there's a few ways we could go about this. We could select an actual real number, say -3 and 4, or pi and 3 over 4, or any of those real numbers we talked about. Or we could keep it more general, because we're talking about any real number, not specific real numbers. So let's remember, real numbers are corresponding to points on the line, right? We've been naming points with letters. So let's consider any real numbers, A and B. Remember, any point on this real number line, this continuum, is a real number. So we can choose any A and any B. Actually, let's erase that. That looks a little too uniform. Let's try to make it not seem like we're picking so close. Let's have B here. So here's our real numbers, A and B. So we're looking at those. They're not equal to each other, so they can't be the same point. A cannot be equal to B. So here's our scenario, the real number line, any two real numbers. Again, these could be spaced here, could be one over here, one over here. It doesn't matter. It doesn't matter. Does there exist a real number C? What are the conditions for that real number C? Such that A is less than that C, and that C is less than B. So are there any real numbers on this line? Or another way to say it, are there any points on this line that would allow C to be greater than A? Well, yeah, all points this side of A, right? What about less than B? Well, all points this side of B. So we're dealing with all points this side of A and this side of B, which would leave this area right there, right? Or this interval. We'll be talking about intervals in our next lesson. So the answer to this first part, is there a real number C such that A is less than C and C is less than B? Well, yeah, there's a lot of them. This whole area could be a real number C. We could choose Dama, point to an area on here for our number C. Okay, perfect, right here. So here's our C. Now this could have been a C to fit that description. This could have been a C to fit that description. This could have been a C to fit that description. This could have been a C to fit that description. In fact, I wonder how many of those there are. I hope it's kind of where this is leading. So the answer to this first part is yes, there is a C. In this case, we're selecting this C. If so, okay, there is, we can move on. Consider points A and C. All right, now we're looking at these 2 points, A and C. Does there exist a real number, C sub 1, such that, similar scenario as to up here, A is less than C sub 1, and C sub 1 is less than C? Or in other words, describing the same scenario we're looking at with C with respect to A and B. Now we're dealing with, is there a real number C sub 1, basically in between A and C, but not being equal to A or not being equal to C? Well, yeah, any real number within this whole area, this whole interval. Any area we pick in here, say right here, fits that description. We can label that C sub 1. It is, A is less than it. A is on this side of C sub 1, but C sub 1 is less than, excuse me, here. But C sub 1 is less than C. It's on this side of C. So kind of, it looks a lot of ways the very same, right? Except, okay, our field of play is shortened. But here's an interesting question. I wonder how many possible points there were for C sub 1 as compared to this longer distance of A and B. Interesting. We'll keep that in the back of our mind. Graphically, let's move on to the next portion. So the answer to both of these first two are yes, there is a real number C such that A is less than C and C is less than B. We chose that one arbitrarily. In which case, we then examined A and C and asked ourselves, is there a real number C sub 1 that is where A is less than C sub 1 and C sub 1 is less than C? And again, we said, yes, there are quite a number of them that we could choose. We arbitrarily chose this one. So using that information, graphically, displaying things graphically, or geometrically may be another good way to say that, does it appear that there always exists a real number between any two real numbers? Recall, real numbers corresponds to a point on a number line. So before we go ahead and answer that, at this point I think it would look like yes. So far, does it appear that there always exists a real number between any two real numbers? Well, that's the scenario we started with. Any two real numbers, was there another real number in between it? Yeah, there was. Then we took two new real numbers. Was there another real number in between that? Well, yes, we got the C sub 1. So let's continue this process a little bit and see if we can get to where we cannot find a real number in between these any two given real numbers. So let's ask ourselves, let's just repeat this, this process we've been doing. Is there a real number, we'll call it C sub 2, that exists between A and C sub 1? Well, yeah, we could choose any. Let's kind of speed up this process, so let's choose a little bit closer to A. Label this C sub 2. So between these two real numbers, there did exist another real number. Well, let's ask ourselves, let's consider between real number A and real number C sub 2. Is there any real number, let's call it C sub 3, that exists between those two numbers? In which case, A is less than C sub 3 and C sub 3 is less than C sub 2. Well, yeah, we could choose. Let's get really close to A this time. Remember, we can't stick on A because that's not what this is saying. So here's C sub 3. All right, now we're narrowing our width. We've got to be getting close to not being able to find a real number, right? We're narrowing it down. So does there exist between between C and C sub 3 a real number or a point on the number line, remember the correspondence, in which a real number exists? We'll call it C sub 4. Well, we could magnify this out, right? This is like taking a magnifying glass. We're looking at this little line, this little portion, and we're allowing our technology, our chalk, to be able to keep up with it a little bit. So this little portion is simply a magnified version of this little portion, in which this point is C and this point is C sub 3. So is there a point or a real number between C and C sub 3 in which another real number exists? Well, yeah, we could choose anywhere in between here. Let's choose right here. Call this C sub 4. Well, between C, or excuse me, not C, this is A. This is why it's important to have good penmanship, which I don't. Between A and C sub 4, is there another real number? Does another real number exist? Well, sure, anywhere between here and here. This process is getting kind of tiring. Let's try to wrap this up. Let's get as closest to A as we can, but it can't be A. There has to be a tiny bit of room between our new point, C sub 5, and A. Well, let's blow it up because we can't really see that close. So we have a new continuum in which this is A and this is C sub 5 we're at. So let's ask ourselves one more time, is there a point or is there a real number between A and C sub 5? Well, yeah, again, there's a lot of them, right? We can get as close to A as we want or to C as we want without being equal to A or C, and that will be another real number, C sub 6. Well, we could blow that up again. Here's A, here's C sub 6. Let's ask ourselves again, is there a real number in between these two real numbers, A and C sub 6, that is not equal to A, not as equal to C 6? Well, yeah, there's an infinite number of points that we could choose from. Remember, this is a continuum. There are no discrete gaps in between. So I think at this point it's safe for us to say, at least geometrically, graphically, that it sure appears that there always exists a real number between any two other real numbers. Let that sink in a little bit. Choose any two real numbers, arbitrarily close to one another without being equal to each other, and there exists another real number such that it is in between, or such that A is less than that real number, which is less than the other endpoint. So good job if you came to that conclusion. It certainly does appear graphically, geometrically, that there always exists a real number between any two real numbers. But perhaps more interesting, or perhaps something to keep your brain churning at night. How many real numbers exist between any two given real numbers? I'll let you kind of consider through this problem. Part of why we're looking at these is it's important, but these are the answer to that next problem, or that next problem that I gave you to consider at night is much beyond the scope of our pre-calculus course. We won't delve into that. But I'm hoping to not just provide information or work through some of these ideas, but to hook you on math, to hook you on some of the things that, to me, are so incredibly interesting and so profound about mathematics, things that will keep your mind wrestling and wrestling and wrestling. And in future courses, perhaps we could look at this and provide an answer to that. How many points are there between any two real numbers? It's quite, I think, surprising and quite remarkable. Consider that we started out with a set gap, so to speak. Well, how many possible real numbers were between that? Well, it appeared that there really could be infinitely many. We narrowed that eventually to a very tiny, tiny, tiny portion of this original area, and we ask ourselves the same question: how many real numbers are between point A and C6 in this case, or C however far down we go? And it still appears there's possibly an infinite number of real numbers. I hope that kind of blows your mind a little bit. I hope that gets you hooked on math. I hope that it'll give you something to consider, a little food for thought in the next days, weeks, months, hopefully years. Look forward to seeing you guys next time as we look further at some of these little line segment type things that we call intervals. We'll see you then.
Thank you for learning with the Fosters. This is a friendly reminder. Remember that these courses are not for free. For information of the cost of the lessons and how to pay, please visit our website. Thank you so much for being with us.